Thank you for coming today. I welcome you with great pleasure. My name is Anna Capucci, I'm the Sowers Embassy. And we organized together with this event is called the Emergent Form in Art and Science. It was conceived by the Art Science Salon in Toronto and organized jointly by the Italian Embassy, the Fields Institute for Research in Mathematical Sciences, and two labs at the University of Toronto, the Center for Drama and the Digital Dramaturgy Lab. We had 3 events already in Toronto. This is the last one here in Ottawa. I feel we wanted something in Ottawa, so there will be also some kind of survey of what is done in the other places. Probably, as you all know, I mean, art and science are two amazing expression of human creativity, and what happens now is that through technology over the years, the distance between these two worlds is becoming narrower and narrower. They are getting more and more near. And so what you see now that it feels like robotics, biosensor, artificial intelligence, even living samples, biological samples, are used, appear into the artistic expression. And here this will be about this, all this discussion today and all this event. And I really hope, actually already happening in some sense, that this is a new way to communicate also science. Difficult concept in science can be expressed also and explained also using art. And okay, I'll leave the voice to Roberta Buiani. She's the artistic curator of the artistic director of the Art Science Salon in Toronto. She will introduce the guest and explain a little bit better how is the flow of the presentations today. Thank you.
So I guess I'm gonna sit there. Okay. Hi everybody. Hi. Is it working? Working? Oh, fantastic. Hi everybody. So my name is Margherita Pevere, and I am super thrilled to be here today. As Anna has mentioned, we are based in Toronto, and this event actually has a special meaning for me. First of all, I'm very happy to be here on the same day as March for Science, which is happening there right now if people are not freezing their butt. And it was like kind of fortuitous, but what a nice day to celebrate the convergence of art and science. The second thing is I have been willing to expand the network here in Ottawa. As you probably know, and especially the people who are in the arts community, it's very difficult to communicate across different cities here in Canada, especially here in Ontario. And this is such a pleasure for me to be here, and I hope that those artists in the audience will actually come to me and talk to me later so that we can actually bring them to Toronto and maybe do something here in Ottawa. So before I start, this is something that we also do in Ottawa, but in Toronto. But I would like to spend like 2 seconds to do a little bit of acknowledgement of the land we are in. I was reading that this is the land of the Algonquin, and we should keep this in mind before we actually do our things. And I do understand that this is about science, about art, but I think there's a big link to the land that we have to acknowledge, and the people who were here and are still here. So. Okay, so you see the website here, the Art Science Salon. The Art Science Salon is an organization, a non-profit organization, founded by me, Roberta Buiani, who I am is the artistic director, and Stephen Morris, who will talk today, who is the scientific director. We are based at the Fields Institute for Research in Mathematical Science, so we are very fortunate. And we have a website, and we have also some cards and some stickers, so you can see this a little bit further. And check us out. We also have a YouTube channel, so you can see our past events. There's another thing that I wanted to show you here. So this year, we were very fortunate to have the support of the Italian Embassy, the Italian Cultural Institute, Fields Institute, Digital Dramaturgy Lab, and the Drama Department at the University of Toronto. And we were fortunate because we were able to bring in international artists. The event, Emergent Form, is a special event, outreach event from the Fields Institute. And it's supposed to celebrate the emergent form that we can find in nature, we can find in the recondite biology, the configuration of the land, the microscopic organisms, or even our body. As you know, our microbiome is a big protagonist in our body. And of course, it spans mathematics, physics, biology, and of course also the arts. So we decided, what a nice occasion to explore this by showing how different perspectives converge in the exploration of emergent form. So I just wanted to show you a couple of images. They're already on. Can you do another assistance? Thank you. Steven, it's like so. Okay. So you will see later. Okay. So we had a series of very, very diverse events. We had a panel, and here you see Stephen Morris presenting his work, and then Luigi Capucci presenting his work at the Fields, a panel. But then we also had a performance which was site-specific. It took the entire atrium of the Fields Institute, and for those people who know what the Fields Institute is, it's a very formal institute of mathematics. So it was very different for them. And we used some specimens. And then we had another performance in a former church turned theater downtown Toronto, and we have this special panel with a lot of people who are involved in artificial intelligence, drone, flying, and other expertise, and robotics and other expertise. If you want to know more information, I can fill you in later. But today, we brought you the international artist and theorist. So I brought you Stephen Morris, who will be the first one to speak. And then I brought you Luigi Capucci, who's a media theorist from Italy. I brought you Margherita Pevere, who is a performing artist and a bioartist and a scholar based in Helsinki. And Donnarumma, who is an artist, scholar, and performer based in Berlin. And Charles Sowers, who is an artist and exhibition designer from the Exploratorium in San Francisco. So we have quite an international panel. So the way this is going to be unfolding is Stephen will go first. Each of the panelists will come here, will have a short presentation of 10 to 15 minutes, and then we will open to the audience and we will have a whole discussion here. So I would like to introduce you to Stephen Morris, who is a professor of physics at the University of Toronto, and he has been specializing in nonlinear physics. And you explain everything, yes, it's too long. Thank you so much.
I've never talked sitting down, so I'm going to stand up. That's all right. Yes, I'm a professor of physics and geophysics at the University of Toronto, and for about 25 years I've been studying what we call pattern formation, which is a kind of emergent form. And slowly, over all those years, I've come to realize that what I'm actually doing is making beautiful art from scientific pictures. So a few years ago, I began to kind of slowly merge my practice, my scientific practice, with art practice. And now I would say I'm about 75% scientist and 25% art person. Or maybe some of them I'm also art organizer, along with Roberto, we organize the Art Sci Salon. So I guess today I'm going to tell you the kind of hard science end of this idea, this rather vague sounding idea of emergent form, and I'm going to try and make that precise for you and show you some examples of emergent form in nature and in the laboratory. What we mean by emergence in science is if you have some kind of complex self-organized structure that arises from within a system with simple parts, but for which you cannot easily guess where that thing comes from by examining the parts. Okay? So if I give you a huge pile of bricks and tell you that it implies a house, then you have to actually assemble the house to find out what the house looks like. You can't just deduce what the house is going to look like from the pile of bricks. If I tell you I have some DNA, you have to go through the whole process of figuring out what kind of cell the DNA produces, and how those cells fit together into tissues, and how those tissues arrange themselves into organs, and how those organs arrange themselves into animals, and how those animals, interact with the environment. There's no shortcut. You can't go straight from the bottom to the top. So at each level of description, there are new concepts that appear, which are called emergent, and those are the emergent forms. And typically, you're basically required to describe things in terms of these non-fundamental steps and emergent things. So for example, here's a Brussels sprout. You're all guessing that it was a cabbage, but no, it's a Brussels sprout. And the Brussels sprout's all wrinkled up inside, and so are lots of plants wrinkled up like this. And if you went to the DNA of the Brussels sprout and asked, okay, so where are the wrinkles? You would find that there's nothing in the DNA that codes for the wrinkles. In fact, two genetically identical Brussels sprouts will have different wrinkles at the different crumple patterns when they grow up. The only appropriate way to talk about crumple patterns is to think of elastic sheets that are under a certain kind of tension or pressure, and how does an elastic sheet crumple. And then it becomes a question of all elastic sheets. So I can show you pictures of rock layers in the earth which are crumpled in exactly the same way as the crumples of the Brussels sprout. If you take a piece of paper and crumple it up in your hand, the rules of that form are just the same as the crumpling in the Brussels sprout. So in some sense, it doesn't matter that it's a Brussels sprout. It's crumpled, and all things crumpled are similar to each other in some kind of deep mathematical way. And the process of crumpling happens at a layer of description which is much larger than the cells or the atoms or the fibers of the paper or whatever your microscopic picture is. And you can't guess what the crumples will look like by trying to start at the bottom. Okay? Don't tell the particle physicists this, because they work really hard to deduce the origin of matter and so on. But basically, you can deduce almost nothing from particle physics except the things that are appropriate to particle physics. You can't even predict the proton, believe it or not. Anyway, so these kind of forms are not amenable to the traditional reductionistic explanation, and typically you have a new hierarchy of language of things I call coherent structures. And coherent structures are like the crumples in the Brussels sprout, and they're the kind of furniture of description that you need to use. And they often exhibit the property of universality, which means that the same coherent structures appear across many different systems, sometimes wildly different from each other, and they require an understanding in their own terms rather than in terms of their microscopic explanation. So what we do scientifically, in summary, is we set up situations where emergent structures happen, and we try to understand their universal properties. Okay? And these properties are just as universal as the laws of particle physics are universal. Okay, so here's an example that you probably all have seen since you live in Ottawa, okay, or you're in Canada. If you look at your typical garden variety icicle, it isn't just a kind of cone or a pointy thing. It actually is decorated by a mysterious ripple pattern. They're often called ribs. And these are pictures of 3 natural icicles. 2 of them grow in my house, okay? And the ripples have very many strange properties. For example, they're always exactly 1 centimeter in width. And we've set up an experiment in my lab in Toronto. We have the world's only icicle growing machine, and we grow icicles and systematically study their morphology, and at the moment we're working very hard on figuring out where the ribs come from, where the ripples come from. And if you want to know anything more about icicles, I urge you to look up my work on it. I put it all online. It's in a thing called the Icicle Atlas. So just Google Icicle Atlas and you'll find it. I'd love to tell you a whole story about these ribs, but the short answer is we do not understand where they come from. There's no obvious mechanism, and there's not even a subtle mechanism that we currently understand. But they are a universal feature of icicles under all temperature conditions, all flow conditions, and so on. They are an emergent, coherent structure. And now that I've told you about them, you're never going to look at icicles the same way again. You're going to be forced to look at those ribs on icicles. So here's a thing I worked on a long time ago. This is a physical experiment where you take a gas layer and you heat it from below and you cool it from above. And it's long been known that when a thing begins to convect, it moves in a kind of jelly roll pattern like this. The fluid flows in a kind of long roll. And the picture is a chaotic state of sort of a tangle of these long rolls of fluid. And you see the beautiful spirals. And I can make a movie of this, and you can watch those spirals evolve in time. So the spirals emerge and disappear and crash into each other. It looks like a kind of self-stirred pot of spaghetti. Okay? Now, the reason I mention this is that there's a different system, which is absolutely completely different in its substrate underlying physics, but it does basically the same thing. If I take a layer, like a plate, and I cover it with a thick layer of sand, and I shake that plate vertically, the sand will begin jumping on the plate until it finally starts to fly around and make little heaps. And those little heaps are kind of in the form of stripe patterns. And if you do things just right, and you use the right kind of depth of sand and frequency and so on, you can actually reproduce the same state, spiral defect chaos, it's called, in bouncing sand. And it's believed that they're completely, at some level, connected to each other. But here, the first experiment, I was heating a fluid from below and having it convect because it gets warm. Here I'm driving grains with a bouncing plate. They seem to be completely unrelated to each other. And at the low level, they are unrelated to each other. But at the level of the pattern, they're universal. Okay? So spiral defect chaos is a universal pattern. It isn't specific to the convection experiment that I showed you before. Here's another shaking experiment that I thought you might enjoy. It's a long plate, and it's shaking vertically away from the screen, so like this. I'm looking down on it, and on it I've put two chains, the kind of chains that are inside your toilet or in when you pull on a light bulb chain. And one of them is colored blue and the other one's colored red, but they're otherwise identical. And as they start shaking, they begin to jiggle around on the plate. And eventually something remarkable happens. They decide, I'm going to be a spiral, what the heck? Okay, and they wind themselves up spontaneously into little spirals. And they're two happy spirals bouncing around. They've completely separated from each other. But later they say, well, we actually like each other, so let's get together. Okay, and they snuggle together for a while, and they kind of have a little bit of complicated motion, and eventually you see they all wrapped inside of each other. It's kind of double spiral, right? See? So there's sort of red, blue spiral inside. Okay, now if I gave you this chain and I gave you the shaker and I said, I asked you to predict what would happen if I did this little experiment, how many of you would have guessed that they would wind into two little spirals like that? Well, the answer is nobody, and no computer in the world could predict it. So here's a beautiful thing called the Bailiff. So those are physics experiments. This is a kind of chemistry experiment. Here I'm going to take a special mixture of chemicals and put them in a petri dish, and you see they don't remain red. They spontaneously, spots start to develop, and little fronts grow. And it looks a bit like growing bacteria or something like that. But really, there's absolutely no biology happening here. These are simple chemical reaction. It turns out this reaction is oscillatory, and it makes waves. And the waves move away from what are called pacemakers, little places where it starts to go. And so when Mr. Belousov first saw this reaction, he was vilified by the chemistry community because they thought he was violating the second law of thermodynamics somehow. But Mr. Zhabotinsky rescued his reputation. And now there are many oscillatory and pattern-forming chemical reactions that are known. Now I'm going to subject you to some mathematics. It turns out that there are very simple equations that you can write down which exhibit all these patterns, or many of these patterns, in a very simple form. And this is a famous one. It's called the Swift-Hohenberg equation. And I've met both Swift and Hohenberg. They're both still alive. And it's, make things brief, it's an equation for a field. That is a thing that fills a plane called phi. And that field depends on both space and time. And what this equation does is it tells phi how to evolve in time. And so the right-hand, left-hand side, from your point of view, is the time derivative of phi. So how should phi change in time? And each term tells phi how to move in a certain way. So the first term, epsilon phi, tells phi to grow exponentially if phi is positive. But the last term, phi cubed, says, minus phi cubed, says if you get too big, it starts shrinking again. And then there's another term, g1, which I can turn on and off. phi squared, which is similar to the phi cubed term. And the gradient squared messy thing in the middle there requires phi to be smooth near neighbors. So phi has to evolve smoothly from place to place. Okay, now if I put in phi equals 0 into that equation, it turns out phi equals 0 is always a solution. So the most boring dynamics is you just start with a plane of nothing, and then nothing happens, okay? But if I put the slightest perturbation, like a little bit of noise in, it turns out the first term causes that noise to grow exponentially, so it's unstable, okay? And then all these other terms begin to happen, and the thing begins to evolve. And let me show you what happens. I can simulate it using this. Can you see it? It's at the top here. Okay, so the phi is color-coded here. For some reason it's not working. It worked before. You know what? We won't do it. We won't do it on the display screen. I think it is. Let me try something else. Let me try. I have a backup one in here. This is a lot higher. No. No. It only works on the screen. You told me to do this, Roberta. This is your idea.
Hey, don't shoot the messenger.
Okay, well,
Plan B.
Plan B. I'll tell you what, I'll show people this after the talk on my laptop. How's that?
Yeah, that's good. That's a good idea.
Okay, well, that's the only way it's going to work. Anyway, what it does is it produces stripes and squares and spots. Okay, so it turns out that what the Swift-Hornberg equation basically produces is stripes. And you can use those equations to simulate the stripe formation on many other creatures, like, for example, stripes on zebras or whatever. So here's this fish, which has a beautiful stripe pattern. And the important thing you'll see if you see the simulation is not only are the stripes there, but they're also imperfect and have these defects in them. And these are two kinds of defects which will actually merge together and annihilate each other. And you can watch those defects move on real fish. And so here's a sand dune pattern, and the sand dune pattern produces a stripe pattern too. And you see there are also defects in the stripe pattern. This one and this one, for example, will approach each other and annihilate. And you can find stripes in rock formation. This is a weird rock called zebra rock from Western Australia. And it has this weird stripes and spots pattern, and no one really understands how it happens. But you can see here's a sort of shattered pile of rubble from the place where the zebra rock comes from, and it's all full of stripes and spots. Probably the most famous spots in the world are spots in vegetation, which occur in dry areas. And in Namibia, there's a place where a large swath of the desert is covered with what are called fairy circles. There are no fairies are involved, actually. But this is kind of scrubby grassland, but there's not enough water to have the grass grow everywhere. And so as you reduce the amount of water in the desert, you might think the whole thing would become a desert at once. But no, it becomes a desert in spots first. So there's a spot with kind of happy grass around the outside of the spot because it's getting more water. And then the inside of the spot is just a completely desert, empty of vegetation. And these spots behave just like the spots in the Swift-Hornberg equation. They merge, they move around, and things like that happen. Another sort of stripe pattern is called a labyrinthine pattern. And this is found on things like brain corals. Okay, so how do you use this? How do you handle this in art? My idea is instead of trying to make a beautiful or make an artistically interesting composition, what you do is you set up a process which has emergence and has emergent pattern formation, and you let it do its thing. You let it self-organize into an emergent form. Here is a mudcrab pattern. And then you exhibit the resulting pattern as art. And because emergent patterns are naturally interesting to the eye, you can use this as a way of producing art which is naturally interesting to look at and also evolves nice in time. And you just let the emergent forms speak for themselves. Thanks very much.
is Luigi Capucci. Luigi is a longtime friend and also former professor of mine, almost professor. We met at the University of Bologna when we both were 20 years younger. So, and he has founded a network based in Europe called Noema, and he is also a publisher and he is a theorist. You will do a very dense presentation. In 15 minutes is going to be a challenge. So thanks for coming here and having this presentation here.
Okay, thank you all for being here. Thank to the Archie Salon for inviting me. Many thanks to the Italian Embassy, the Italian Cultural Institute, and the Field Institute in Toronto. There are a lot of people that we should thank, but I think that maybe we will do in the end of my presentation. Well, I want to start my presentation with some consideration about life. That appears as a complex and elusive entity, and life in history has always been considered as inherent to the organic realm, and in particular a carbon-based entity, and since the end of the 18th century, it was known that the organic matter contains carbon and hydrogen, and also oxygen, nitrogen, and phosphorus. Subsequently, the organic and carbon-based idea of life on Earth has been extrapolated as the universal one, and when scientists are wondering about life in the universe, they base their models on organic compound. The most intriguing among life's characteristics probably is elusiveness. Many disciplines have tried to define it. Here you can find some definitions, but none can be considered exhaustive. What makes a conglomeration of chemicals or a mass of matter a living organism? Viruses are an example of this uncertain situation, since they are located at the border between organic chemistry and life. And for decades, the scientists have debated whether they should be considered as living or not. These ancient entities can affect all life form on Earth and often determine those that will survive. Viruses are responsible for birth and extinction of species. They are pollinators of genes and trainers of evolution. According to Luis Villarreal, director of the Virus Resistance Center at the University of California in Irvine, so life itself is an emergent complex state, but it is made from the same fundamental physical building blocks that constitute a virus. Approached from this perspective, viruses, though not fully alive, may be thought of as being more than inert matter. They verge on life. This verging on life sounds intriguing to me. Is life a sort of terminus ad quem, some attracting asymptote? Is it anything to which matter is tending? Is it a particular state of matter? According to genetics, every individual, whatever the species to which it belongs, is unique. Though all individuals are pervaded by the same matter and processes, the geneticist Edoardo Boncinelli writes, many discoveries have brought to light the incredible unity of human beings. The fundamental processes and mechanisms that control them are essentially the same in all species. It turned out, for example, that to make a sturgeon, a frog, a mouse, or a man, this requires the programming and coordinating action of a number of different genes which the animals of all these species have in common, and which are also in the genetic heritage of insects and shellfish. Hence, life seems a sort of continuum, where all the living beings are related, and in fact, the division of species from this continuum is a difficult and often an arbitrary task.
In my practice, I employ a constellation of strategies which bring me from the artist studio to the scientific laboratory and back. to the academic field. So, as you can imagine, my work is also based on collaborations, and I collaborate with scientists, bioscientists, biohackers, the audience, as we did at Fields Institute, and with a variety of organisms. What I will do today with you is to show you some artworks, some recent artworks that feature various degrees of collaborations and complexity, and they are all related to my travel to Canada. What we see here is Skin Studies, as a work that I have realized this year, in 2018, and I show this to you because we should have exhibited in, at Fields Institute for Roberta's project that occupies the cabinets of the Scientific Institute, showing artworks instead of scientific exhibits. But unfortunately, the work got stuck somewhere in Germany. The shipping didn't arrive in time, and so I'm sorry, we couldn't exhibit the works. I don't know how much you can see on the screen, but what you see is a sample of microbial cellulose that is mounted on Japanese papier and pinned to the wall, or in this case it was a frame. And can you see it on the, because here I have a different refraction angle. Okay, glad to know it works. And the samples you see are microbial cellulose. Microbial cellulose is a biofilm produced by a variety of organisms, algae and bacteria, for example. In some cases, it's also it can be problematic from human health because some pathogen bacteria produce this biofilm in medical devices, for example, in hospital, or you can have biofilm in your mouth if your oral hygiene is not good enough. And biofilm is a way bacterial colonies have to protect themselves from external agents. And it's still not clear how they start. It is not exactly clear why they make it, so protection is one guess, but we don't exactly know. And it's also not clear how the communication works among the single bacteria who at a certain point in time grow and gain a critical mass to produce this biofilm. Probably there is some quorum sensing involved. Quorum sensing is a strategy of communication in bacteria that produces certain enzymes that are released in an environment, and if each cell receives enough enzymes, then all bacteria are aware that there are enough of them, and they can start either building something or carry on an attack on the host organism. And microbial cellulose is a material that is involved and that is used also in biomedical sciences for patches, or also in high-end speakers because of some technical properties and flexibility under certain conditions. And what is remarkable is also its resemblance to human, or to body matter and to skin. So this work is a tribute to this ambiguity of the material that is produced by bacteria, but at the same time reminds us uncannily of our bodily existence. This is another sample. So the previous ones are 14 per 21 centimeters, and this one is 48 per 21 centimeters. And in this case, the sample grew in more or less 1 week time, where these little ones are younger, or they grew for a short time. What's interesting of this material is that it grows on the surface and covers all the available surface. So it doesn't depend on the quantity, doesn't depend on the speed of the growth depends on the concentration of the nutrients in the medium, but the size depends on the size of the container. So if you have a container that is this big, this is the sample you're gonna get. But if you have a tray that is big as this table, then you have this size. And the next work I'm going to show you is called lymph. It's a work I realized 2 years ago, and it was commissioned by State Festival in Berlin. It's a festival for open science with also a special interest for arts, and which was curated by Daniela Silvestrin, another curator who also collaborated with Roberta a few years ago. And Daniela commissioned me a work that had to deal with the sense of disgust, because the festival theme was the senses, so you have the sight, the smell, and it was emotions. Sorry, I got confused because I used them, the smell. It was emotions, so the happiness and all. She had different works exploring each other one of the 7 emotions, and she commissioned me. I'm sorry, I got stuck with my own words. She commissioned me a work on the sense of the emotion of disgust, because we thought that the materiality of my artistic practice responds well to the emergence of this emotion. And what I did was to combine a fairly classical shape, a fairly classical aesthetic with materials that are either controversial or considered disgusting. We should consider that disgust is the physiological underpinning phenomenon to abjection, but abjection is culturally informed. For example, some cultures eat pig meat and some others avoid pork because it's contaminated or disgusting. Whereas disgust is the physiological reaction that you have, for example, when you smell something that triggers specific neuroreceptors, and you either step back, or you hold your breath, or you wrinkle your nose. These are all typical behavior patterns that are related to disgust. As I mentioned, I work with materials that were controversial, and I worked on an aesthetic overlapping of a pigment that was used back in the centuries, especially in Baroque times, which is called caput mortuum. Caput mortuum is a word from alchemy that means the last remains after the sublimation process. So once you transform the materials, the very last remains that can't be used for anything else are called caput mortuum. And strikingly, it's a very beautiful color, and it was said to be made with mummies, with ground mummies. Then when the thing came up back in the centuries, they switched to the production of this pigment based on iron oxides. And strikingly, it's the same color with a material that is utterly controversial today, which is blood meal. Blood meal is the last remaining of the industrial farming. It's the blood of animals that are slaughtered. In some cases, the blood is separated, and for example, serum is used for cosmetic industry, whereas the red part of the blood can be used for any purposes In some cases it's used for food production, like blood sausages, but the big part of it is used for fertilizers. But not only. Before BSS, this mad cow disease that outburst a few years ago, because animals were fed with dead animals, despite being herbivores. This blood meal was amongst the components of this animal food, and for this reason, the general audience associates it with the outburst of the disease, but actually it's not related to that as a fertilizer, because it's very rich in potassium and it's sold as an organic fertilizer. So when you go to the shop, you buy organically farmed, you know that probably crops has been fertilized with blood meal. And there is also an economic aspect to that, since at least in Europe, some countries overproduce farming and have to export the industrial discards like animal blood or manure, because the production is too high for the agricultural system to absorb that. And I found interesting how these two materials are controversial for different reasons, but the objection related to that depended much on the context where they were observed. And the smell of this animal blood meal is so strong and intense that you immediately step back. And so the work emerged through the time of the exhibition, in the sense that I prepared a dripping system that slowly dripped and stained this cloth, emanating the smell. This is a detail with a container with some smelly blood meals and some vertebrae. This is a project I'm currently working at, so I'm glad to show you a prototype. It's not its final shape. And there were a series, the series is called Wombs, and it's a reflection on sexuality and desires and fears behind maternity. And it starts from my own personal experience. It's probably the first autobiographical work I do, and it addresses how oral contraceptives are processed by our bodies and then discarded in the environment, producing chemical and molecular pollution that collects then in aquatic environment and might affect the life of other organisms. It's a topic that is still addressed too little. Of course, it's not only human contraceptives that are responsible for this phenomena, but also the huge amount of hormones that is used for farming and production of food. And the final version will comprise living bacterial cultures. It's the same bacterial cultures that you saw in the first works, but in this case it's pigmented. And I will have it growing in the open glassware, and slowly there will be a pollution process. So I will extract my own hormones. Abbiamo finito il tempo. Oh, I'm sorry. Okay. And I will very quickly go to the work that I presented for Outside Salon. It's called Anatomy of an Interconnected System, and it brings together the reflection that I've been doing in the previous artworks in a performative session that emerged thanks to the participation of the audience. Yes. Thank you.
Okay. Unfortunately, we don't have a lot of time, and we are caught into this like passionate discourse. So I would like to call the next speaker, Marco Donnarumma, who is also a performer, and he did this incredibly emotional and intense performance on Thursday night at the theater. And he will show us not just the work that he did on Thursday, but he will also talk a little bit about his further development with his new installations. Thanks.
Thank you. Let me just get my... Alright, so, well, once again, customary thanks to the Embassy, the Fields Institute, to Roberta Salon and Stephen for organizing this and allowing our trip from Germany to Canada. So, this is me, and I'm originally from Italy, based in Berlin, and I'm an artist working as a strange crossroads between contemporary performance and media art. I'm a performer myself, and that's my main way of expression. When I don't perform, I get kind of depressed, so I need to move. And my main focus is about the relation between body, technology, and sound. And I do believe that this relationship between them yields a certain kind of politics. Politics around our own understanding of what a body is and what a body is capable of. So my main point in the recent years is to try and use technology to tear apart the idea that the human body is a fixed entity. The idea of a normal body is a cultural construct. It depends on the context where it takes shape, and it can be dismantled as well. So that's what I try to do in my work. And I'm gonna talk about my most recent endeavors. I'm working since the early 2000s, and I developed a particular practice using sensors that capture signals from the body, coupling these sensors with particular sound system configurations, using also acoustic effects in the venue where I played in order to influence the body of the audience as well. And then more recently, I started using, together with my interactive music system, I started working with artificial intelligence and robotics. And so I'm gonna talk about this particular area of my practice. So I will start by showing you a video. This is called Corpus Nil, and it's an experimental dance performance where I use different kind of sensors on my body to analyze the muscular activity of my body as it moves. And while I perform this particular choreography, but then what happens is that I'm performing together with an artificial intelligence software that produces the sound and the light patterns that emphasize the kind of body that you see there on stage. And what interests me there is how you can create tangible experiences of alternative bodies. What I mean by tangible experiences of alternative bodies. So what you've just seen in the video is what you actually experience in the theater. So it is a speculation about bodily form that can arise from the conjunction of flesh and circuitry. But it's not only a mental speculation, it's a physical embodiment. So that's my body there on stage, using some particular makeup that erase part of my body by painting them in black, and having the software producing this particular sound and light. Then what remains, it's this kind of fleshly things that live there on stage, just in front of your eyes. And additionally, I use a particular instrument that captures sounds from muscular activity. So you can think of the heartbeat, it's the sound of the muscle of the heart pulsing. So I capture those kind of sounds from my muscles and from the blood flowing in the vein, and amplify those sounds in the room. And what you hear then is kind of a very low rumble that submerges the audience and then resonates also the space when it's properly amplified. And in this way, the sounds from my body kind of enter the bodies of the audience as well. And this is one mechanism that I use to engage physically the audience in what I do. This piece emerges from my research into body theory, which is a cultural study of the body. This is something I started during my PhD some years ago. I was studying at Goldsmith in London. I was doing this weird PhD between computing, performance art, and body theory. And so a great inspiration from my work came from work of authors such as Margaret Shildrick and Lisa Blackman, who specialize in feminist studies and disability studies, which is really fascinating because it tells a lot about the way we understand monstruosity and abjection and abnormality in the bodies of others, and how that condition the way we perceive our own body as well, and the way we treat others around us. So by analyzing this kind of notion and then performing this work, then I started feeling I needed something else to broach these kind of questions. So whether in Corpus Nil I'm performing with this artificial intelligence software, I have nothing to touch, I have nothing to perform with there. So what the action of the software are disembodied. And so I started working with a laboratory of neurorobotics in Berlin, and they develop humanoid robots. So they develop robots that look like children, because they want to study the way the robots develop its own form of intelligence. And this is pretty fascinating. So what I did, I convinced them to let me use their platforms from robotics, and here is the result. Oh no, that's something else. this is obviously not something that I could do by myself, and in fact here you can see all the people that participated in this thing. So we basically have a team of about 13 people working on this. It's a highly transdisciplinary team, and that's also the lack of being in a place like Berlin.
I was trying to figure out what the material, what I could use as a material in there. I was thinking it had something to do with like the density of mud and the density of water, and I was sort of racking my brain and looking at density matched polyethylene beads, and finally it dawned on me that I could use something natural. I could actually just go and retrieve the mud puddle. And it's the perfect stuff, the clay and the mud and all that. And so, I did some experiments just trying to understand. I thought maybe it was just naturally separating. I put a hot light on it and I was measuring some temperature and stuff. And I finally came to this conclusion that what was happening was that the mud puddle overnight had cooled down, and then hot or warm water in the morning there was water flowing down this pavement. And I think it was warming up, and so it was just flowing over the top. And this is a sort of an interface layer between a clear fluid and a turbid, clay-filled fluid. And you get those waves. And so I proved that in a sink by putting a little bit of the mud puddle in this basin and running hot water over it. And that's as far as I've gotten on it. But I use it to sort of illustrate what I try to do, because I think that for me, well, I'm a little bit, I think I'm a little bit self-indulgent. I just like beautiful things, and there's nothing more beautiful than what I find in the natural world. And there's so many surprises and mysteries to me that it just occupies me entirely. And so I spent time recreating phenomena, I guess. This is a machine that allows you to watch ice form on a window, basically. And it's a horizontal plate, and there is coolant flowing through it, and you view it through cross polarizers. Oh, and I don't need the sound. If you could just, yeah. A lot of my videos are sort of, I don't know, they're not professionally produced, so. The processes that Stephen talked about of pattern formation play into the work that I'm interested in, because I find that there are so many mysteries in nature, and a lot of it has to do with how does it know how to create the forms that it creates. And so in this case, what you saw at first was super cooled water, and I could actually touch it and create nucleation points for the ice to start forming. And then this case is a separate situation where you melt a spot, and then around the edges it starts growing back. And the way these two different forms of ice are very different. You can see around the far edges there's this sort of ropey, which was the super cooled crystal form, and then you see what's growing into the center are large, like feather-like flakes or plates of ice. And this is all real time, and this is one of the things about this is that I work at this place that is a sort of intersection of science and art called the Exploratorium. And so this is on display for anyone to do at any, and we have over 1.5 million visitors a year. So these are all set up for people to manipulate themselves. So it's not to just create, a video or something like that. It's to witness it over and over and over. I'm going to use this thing. I have to turn it on. What's the center? This is just to show you what the apparatus is. There's coolant that flows in this glass tank, and then you put water on the surface, and there's a light box underneath with a polarizer and a polarizing filter above. And center position. All right, never mind. This is ferrofluid. Ferrofluid trapped between two glass plates, and there is a competition of forces between the fluid forces that want to hold the ferrofluid together and the magnetic forces that want to make it come apart. And so it's a flat plate, there's a light box underneath, you put a magnet underneath and you move it around and you get these patterns. And so maybe you don't see this out in the world, you see labyrinthine kind of things and rain coral, but it does something strange when it's constrained, in certain circumstances. And that's what it manifests as, is this little table that you can sit with somebody and explore together. And a fluid experience, I guess. This is what's kind of called a stream table. These objects in the flow create these regular vortices, and then that's called a vortex street. And people can place these objects in and change the flow and get different speeds of flow and things like that. Also in that same vein is, this is a scanned fog. It's been scanned with a laser, and you see the black bar because of the mismatch in speed between the shutter of the camera and the scanning laser. And what people are often surprised because they think it looks like a liquid, and they tentatively touch it and then find their hands are dry. And it takes them a moment to kind of understand what's going on. And it's a really beautiful place to be for people to be in that position of almost understanding it and then understanding, because they don't always jump to, they have to ponder it a little more than they would have. I think like Marco's piece where you can't tell it's his body exactly and what is that? I think those moments make you think more than when you immediately recognize it. And that is also the form. This next piece is well, this chamber here is filled with fluid, and this whole top part, the whole chamber and this screen rotate, and there's a light down below. So you flip it over, and then in this case you flip it back up, and then drips form from the top and drip down. And when you project the light through it, you get these what are called caustics, and they're very pretty, and they're engaging to watch. So again, well, so one of the questions is sort of in that I find interesting is that one of the things is that drips tend to form out into regular hexagons. So you start to see it here. You see the sort of boundaries of these circles are hexagonal. And the question is sort of, how does that know to do that? And which is a curious question, and it's not one that I necessarily get into, but I just allow people to experience it. And so like I said, I'm a little bit just. And then there's this issue where you saw that right there, that when you first flip it over, it has to figure out where to go, and it has an interesting state there at the beginning that I really enjoy. Also, as Stephen said, I've never gotten spiral defect chaos out of this, but this is shaking sand, and there are all kinds of patterns. I don't know if that's, you see some of the movement, and it's controlled with an iPad interface, so you can, by varying the volume and the frequency of the shaking, you get all kinds of different patterns in it. And again, this is something people just can sit down and do and experience. And part of maybe why I don't take too many videos of it and all that is that it's sort of always there. It's not a temporal thing for me. And I'm gonna, so that's the apparatus, that's the iPad interface with the amplitude on the Y and the volume on the X, or actually, yeah, I mean the frequency on the X. So here's sort of a bunch of pictures of the kinds of patterns that you can get out of it. And also, if you vibrate water, you get all kinds of patterns, or fluid. And even a big basin of fluid looking up through this lenticular shape. When I was making the scanning fog piece, I was always intrigued just by the fog itself. And I spent a long time trying to figure out how to show people what I was seeing in it. And then around this time, strip LEDs started becoming easily available, and it really just made it work. Before that, I would just stick like halogen lights in and things, and you just could never see it. And then this made all that structure that's going on in the fog visible. And I look for these things that are like fireplaces or whatever, that have lots of motion and are hypnotic and allow you to see these things. This is a basin filled with water and sand on the bottom, and when you shimmy it back and forth, you get lots of patterns, like the sand dunes in a way. And here is a smaller version. It's a much thinner cell, and also you get patterns. A lot of what I do is try to make people see things that they don't normally notice. So this is a mirror that is at 45 degrees and is reflecting the zenith sky, which is deep blue. And then there's inset, a small mirror that moves in and out, and it's controlled at this pedestal. And this small mirror shows the difference between that zenith sky and the horizon sky. And the horizon sky is much lighter than the zenith sky. And usually if you ask somebody what color's the sky, they just say blue, and they don't even look at it really. They haven't noticed that it's different from horizon to zenith. In 2006, I had the opportunity to work at LIGO, the Laser Interferometry Gravity Wave Observatory, which recently actually measured gravity waves, and they were building a education center, and I had the good fortune to be able to work on the outside with some colleagues of mine, Peter Richard and Sean Lonnie. And so these are rows of just aluminum tubes that pivot a little below, or a little above center, and then this is a row of magnets that couple them together. And so the wind moves these along, and when one moves, the magnets make the neighbor move. Okay. And I'll just end with this piece, which is a wind piece. There's 612 wind directional arrows on this building, and they just map out the direction of the wind, and you see how the wind resolves and with the architecture of the building. And what I do is really, I think a lot of what I try to do is just set the conditions for the natural world to complete, and so that people can appreciate the beauty that's in the world.
Where is that building?
This is in San Francisco. Okay.
So I'm calling all the panelists, and we're going to have a Q&A and possibly a discussion. We have some time before we start having, there will be a reception after this, so stay with us. So is there any question from the audience for our artist? Yes.
Yes, I'd like to ask the person who's living in Berlin doing her PhD in Helsinki. Images that you showed obviously were on some kind of paper. Was that a photographic image, or was that the skin or the material that you had grown? If you could just describe that a little more. Thank you.
Yeah, sure. So in the first picture,
And sorry, can you also remind me of your name?
yes, sure, Margherita Pevere. I can give you a flyer later, so you also get the right spelling of the name, which has various versions across the world, I've realized. So maybe, Stephen, may we show the first picture of the presentation? It's the actual material, it's the actual biofilm.
Okay.
So the biofilm grows on the liquid medium, and if you take out of the liquid, it dries. Then you can treat it, coat it, and to preserve its flexibility. Otherwise, it would brittle. And I stuck the biofilm to the Japanese papier and pinned it on the background. And it sticks by itself on paper because of the very similar materials that are highly compatible. So what you see here, it's 4 pieces of paper, and the biofilm samples are stuck on them.
Thank you very much.
Thank you. Or maybe mounted would be a softer word.
Stuck.
Yeah, but actually they stick.
Yeah. So,
whoever wants to consider it. Has any of this work informed your sense of the ethics we should be developing? Has any of this work given you ideas about the ethics that we should be developing as we move further and further to merging, robotics and human, or the transgenic world that we're moving towards?
I've never had to consider ethics because I never study anything that's alive. If you want to study anything that's alive at a university, in a university setting, you have to go through all sorts of ethics considerations, and that's quite a big barrier to scientific research in those fields. So for that reason, there are kind of institutional barriers to doing anything that could even be remotely considered unethical. So that tends to keep academic scientists from doing animal studies unless they're very serious about it. And I'm never that serious, so I don't do it.
So if I may, let's go in order. But if I may, I don't present anything, but one of the goals of the RSI Salon is to have artists and scientists, to foster collaborations between artists and scientists. And I think that ethics is one of the most important things that we should be considering. Because of course the scientists, especially when they are institutionalized, meaning they're not crazy, but they are embedded in an institution, are all subject to ethics committee, and whenever they write a grant, they have to go through all these rules and regulations, and they have to comply with the ethics of the university. But in the case, but there's also a lot of independent scientists, and there's also a lot of independent artists. Actually, as a matter of fact, most artists are independent. And one of the things that we would like to do is to demonstrate that when you're doing research, you're not just doing science, you're also doing social science, you're also doing art, because research also resides in the arts, and you need to consider ethics, and you also need to inform each other's ethics. I think that this, like having a dialogue not just across disciplines but across the arts and science, would actually inform both scientists and artists about reciprocal ethics and also reciprocal respect. And I think there's a lot to learn. I think that there's a mutual exchange that can be had. So this is one of the goals of the Artside Salon. So, okay, so Margherita.
Yeah, I think Roberta has given a wonderful overview of the complexity of the topic. So we should probably make a series of conferences on that to expand it properly. But I can say that working with living matter, ethics is one of the most important parts of it, and it requires a good amount of thinking, good amount of awareness, and it also gives insight on how complex the topic is, because, for example, working with bacterial cultures doesn't raise so many ethical questions actually in the audience, but as soon as you have a so-called more complex organism, for example an animal in your artwork, then you start receiving the hate mails, you have to deal with animal rights groups, which can also get very aggressive. And this I know from the experience of work of colleagues of mine working directly with that. So my point as an artist could be that we need to address the topic broadly, and I welcome controversial artworks because they show our ambivalence, because we don't question if working with bacteria is ethical, whereas we do when we work with animals, and why that difference. Moreover, we start questioning the use of animals or living matter in general in the arts, whereas we don't question, for example, how electricity and digital technology can affect the ecosystem, which is one of the main activities that affect resource extraction and pollution. But we don't wonder in a digital installation if this is ethical or not. And my personal take on this is that there's a lot to discuss, because I see there is a bit of ambiguity.
Well, I think that your question is a very important question, a very important issue. And I think that the more we study growing knowledge in knowledge of the world, knowledge of the animals, knowledge of the ecosystem, awareness of being here, we realize that we have a very important clue on the environment and on the world that we live in. And probably we are, it is not clear how we can match with this. Because some people tell that we should stop what we are doing, but the history of humanity shows that it did never stop, and unless there are some natural or human caused wars and so on. So. Anyway, I think that it is very important to introduce, especially inside the studies, scientific studies, the ethical questions, ethical issues. And in particular, as I told in Toronto, as I said in Toronto, there is a movement in the States that is growing worldwide that adds art studies inside the scientific curriculum. the movement is sometimes called from STEM. STEM is science, technology, engineering, and mathematics, to STEAM, scientific, technology, engineering, arts, and mathematics. Because arts can bring some kind of critical view, can help in seeing what you are doing in the scientific realm with a wider point of view. I think, and I conclude that we should also try to change some, and it will be very difficult in the future to change our viewpoint and change paradigm.